Somewhere off the coast of Oregon, in complete darkness, 4,000 feet beneath the waves, a research ship made a navigational error that would rewrite this. But when scientists later examined the data collected from that unplanned detour, they noticed something buried in the seafloor that didn't belong there. A pattern in the sediment layers, stacked like the rings of a tree, recording a secret the Earth had been keeping for thousands of years. Two fault systems, thought to operate independently, may be talking to each other. And when one speaks, the other may answer. This is the story of what lies beneath the ground that 50 million Americans call home. Not a hypothetical, not a movie plot, a geological structure, mapped in exacting detail only in the last 2 years, using data 10 times sharper than anything scientists had before. Tohoku disaster and every hurricane in recorded American history combined. For 40 years, the public was told the danger was known, mapped, and understood. They were wrong, because the instruments scientists were using were built in the 1980s. The models were built on guesses. And underneath one of the most seismically dangerous stretches of coastline on the planet, the Earth has been rearranging itself in ways nobody detected, until now. This is the story of the Cascadia subduction zone, the place where the Pacific Northwest ends and an unknown future begins. To understand why scientists are suddenly terrified of something that has existed for millions of years, you have to understand what is actually happening beneath the waves of the Pacific Ocean, 700 miles off the coasts of Washington, Oregon, and Northern California. There, the Juan de Fuca Plate, a slab of ocean floor roughly the size of Great Britain, is being forced beneath the North American continent. Not gently, not smoothly. It is locked, frozen in place by immense friction, unable to slide, while the converge by roughly the width of a fingernail. And every year, that tiny motion doesn't release stress. It stores it. For 300 years, that stress has been accumulating without a single major release, which means the ground beneath Seattle, Portland, and dozens of coastal towns has been compressing like a spring, coiling tighter and tighter, waiting. Geologists have a name for this kind of fault. They call it a megathrust, the same type of fault responsible for the 2011 Tohoku earthquake in Japan, which triggered a tsunami that erased entire towns from the map in minutes. The same type of fault. Behind the 2004 Indian Ocean earthquake, one of the deadliest natural disasters in human history. And Cascadia is capable of producing an earthquake in that same range. Magnitude 9, possibly higher. We know this not from speculation, but from the ground itself. Buried in the marshlands along the Pacific coast are ghost forests, stands of dead cedar trees still standing. Upright, drowned in salt water more than 3 centuries ago when the coastline suddenly dropped several feet in an instant. Japanese scrolls from the same era describe a tsunami that arrived with no warning earthquake of its own, a mystery for 200 years, until scientists on the other side of the Pacific realized they were reading the aftershock of a monster born in Cascadia. The date has now been pinned down with unnerving precision. January 26, 1700, 9 o'clock at night, local Japanese time. That is when the last full-length rupture of the Cascadia subduction zone occurred. An earthquake so massive it sent a tsunami racing across an entire ocean, striking Japan. The earthquake actually happened. For 326 years, the fault beneath the Pacific Northwest has stayed silent. But silence is not the same as safety. In fault mechanics, silence is a warning. And in the last 2 years, that warning has become impossible to ignore. In 2021, a research ship called the Marcus G. Langseth set out on a 41-day expedition led by marine geophysicist Suzanne Carbot of Columbia University's Lamont Doherty Earth Observatory. Towing a sensor array over 9 miles long behind the vessel, the team fired sound pulses into the seafloor and listened for the echoes bouncing back from miles beneath the crust. A process not unlike using sonar to map the inside of the Earth itself. What came back, published in 2024, replaced 4 decades of assumptions with the sharpest image of the Cascadia Fault ever produced. And the picture was not what anyone expected. The fault does not behave as one continuous, unified system as older models assumed. It fractures into at least 4 distinct segments, separated by massive perpendicular faults running crosswise through the subduction zone. Geological seams that may act like circuit breakers, potentially limiting how far a single rupture can travel. That should have been reassuring news. A segmented fault, in theory, produces smaller, more contained earthquakes. Except one segment broke every rule. Stretching from southern Vancouver Island down through Washington State, this section of the fault is unusually flat and smooth. Elsewhere along Cascadia, subducted seamounts, undersea mountains dragged down with the sinking plate, create rough, irregular surfaces that can interrupt and stop a rupture before it spreads too far. This segment has none of that texture. Nothing to slow it down, nothing to stop it. Which means according to researchers who spent decades studying subduction zones around the world, that this is exactly the kind of structure known to produce the largest earthquakes on Earth. A single, unbroken, unstoppable failure, from Vancouver Island to central Washington, releasing centuries of stored energy in one continuous rupture. And that was only the beginning of what the new data revealed. Because while Carbata's team was mapping the deep offshore fault, a separate discovery was unfolding much closer to shore, directly beneath one of the most densely populated regions in the entire Pacific Northwest, Seattle. Running east to west, directly under the city and the communities surrounding it, lies the Seattle Fault Zone, long known to scientists, but long underestimated. The main fault produces major earthquakes only rarely, on cycles longer than 5,000 years. For decades, that gave planners a sense of manageable, distant risk. But newer research, published in the Geological Society of America Bulletin, uncovered something the original models missed entirely: a network of smaller secondary faults branching off the main system, threading beneath Bainbridge Island and the neighborhoods of Greater Seattle. These faults are so short that under the current National Seismic Hazard Model, they don't meet the minimum length requirement to even be counted. The government's own hazard calculations, the ones used to set building codes and emergency planning across an entire region, are leaving them out, not because they're harmless, but because the models were never built to see them. According to Stephen Angster, one of the geologists behind the discovery, that emission may be hiding an entire category of danger the public has never been warned about. Shorter faults close to the surface can rupture with less total energy than a megathrust event. But because they sit directly beneath population centers, with almost no distance to soften the shaking before it reaches homes, hospitals, and highways, their local destructive potential can rival much larger, more distant earthquakes. In other words, it isn't only the sleeping giant offshore that Seattle needs to fear. It's the smaller cracks running silently beneath its own foundations. And 400 miles south, in Northern California, a third piece of this expanding puzzle was falling into place, one that had puzzled scientists for over 70 years. In 1954, a powerful earthquake struck near Humboldt Bay in Northern California, and for decades, it simply didn't make sense. Most earthquakes in that region originate from the nearby Gorda Plate, a smaller, chaotic fragment of oceanic crust known for its complicated, unpredictable rupture patterns. But the 1954 quake didn't match that signature. It took modern data, modern models, and a fresh look at old eyewitness records for researchers to finally understand what happened that year. The quake, they now believe, didn't originate on the Gorda Plate at all. It came from the Cascadia subduction interface itself, the same fault capable of producing the magnitude 9 monster of 1700, which means Cascadia isn't only capable of the big one, it may also be capable of breaking in smaller, unexpected ways scientists never accounted for, a fault with more moods, more behaviors, and more unpredictability than anyone previously modeled. And just south of that mystery, at the point where 3 tectonic plates collide in one of the most geologically chaotic zones on the continent, the Mendocino Triple Junction, scientists using tidal stress modeling uncovered something else entirely. A chunk of the North American plate has broken off. It's being dragged downward with the subducting Gorda Plate, sinking into the mantle in a piece separate from the plate around it. Researchers confirmed the existence of what they now call the Pioneer Fragment, a slab of older rock being pulled under the continent in a process previously only theorized. Crucially, this new data revealed that the subducting surface sits shallower than earlier. Models assumed, meaning scientists have to redraw the actual boundary of one of the most dangerous plate junctions on Earth. The fault system needed to be completely redrawn. What else has gone undetected for that long, underneath the rest of the country? And then, in 2026, came the discovery that connected everything. Buried in the underwater sediment off the Oregon coast, the same sediment layers that first hinted at the 1700 earthquake. Researchers uncovered evidence of something no model had predicted. Paired layers, deposited by underwater landslides, showing that ruptures along Cascadia and ruptures along California's San Andreas Fault may have occurred in close succession, not once, but repeatedly over thousands of years. 2 of the most dangerous fault systems in the United States, long studied and modeled separately, may not be separate at all. They may be connected, capable of triggering each other in a chain reaction stretching almost the entire length of the West Coast within a span of hours. If that pattern repeats, a single Cascadia megaquake wouldn't just devastate the Pacific Northwest. It could set off a second catastrophic rupture along California's San Andreas Fault, a fault already under record stress. In fact, a separate 2026 study found that Southern California's fault system, particularly a critical junction geologists call the Earthquake Gate near Kagan Pass, is more stressed right now than at any point in the past 1,000 years, a gate under the highest pressure it has experienced in a millennium. sitting less than a day's rupture away from a fault system that may be able to reach out and pull the trigger. This is not a science fiction premise. This is published, peer-reviewed research released across 2025 and 2026, rewriting what, in the span of just 2 years, that assumption collapsed. A ship's navigational error revealed a hidden connection between two fault systems separated by hundreds of miles. Sonar technology exposed a segmented fault structure nobody had previously confirmed. A network of secondary faults beneath one of America's largest cities turned out to be excluded from national hazard models. A 70-year-old earthquake mystery was finally solved, revealing that Cascadia behaves in ways far stranger than anyone assumed. And a broken fragment of tectonic plate, silently sinking beneath the continent, forced scientists to redraw the boundary of one of the most dangerous junctions in North America. Every one of those discoveries happened using instruments and techniques that did not exist, or were not yet applied to this region before the 2020s. Which means the geological understanding beneath your feet, beneath entire American cities, has been rewritten within the last handful of years. Not decades ago, not in a distant academic era, now, in your lifetime, preparing to fail, buying communities crucial minutes or even hours of warning before the ground begins to move. But today, that technology does not yet exist in a form that can reliably predict the timing of a Cascadia rupture. Today, the only tool available is knowledge, an understanding of what lies beneath passed from scientists to the public, in the hope that awareness itself becomes a form of preparation. Because somewhere beneath the waves off Oregon, the fault is still locked, still compressing, still storing, silently, second by second, the same kind of energy that once sent a tsunami racing across the entire width of the Pacific Ocean, striking the shores of Japan without warning 326 years ago. And somewhere beneath Seattle, smaller faults that were never supposed to matter are quietly rewriting what major earthquake even means for a modern American city. And south of that, near a triple junction where 3 tectonic plates grind against one another, a broken fragment of continent continues its slow descent into the Earth's mantle. Evidence that even the ground we assume is solid, permanent, and unchanging is in fact constantly moving, breaking, and reshaping itself beneath our feet. We build our cities on the assumption of stillness. We plan our lives, our infrastructure, our futures, as though the ground beneath us is a fixed and finished thing. It never was. It never will be. Every discovery revealed in this story is a reminder that the Earth is not a static backdrop to human civilization. It is an active, restless living system, indifferent to the cities we've built on top of it, following a clock that operates on a timescale almost impossible for the human mind to fully grasp. 300 years feels, to us, like an eternity. To the Cascadia subduction zone, it is simply the space between one breath and the next. The last time this fault released the energy it has been storing, no one in North America had ever seen a steam engine, an electric light, or a telephone. There was no United States of America. The city of Seattle would not exist for another century and a half. Today, that same fault sits beneath a skyline of glass towers, beneath the offices of the world's largest technology companies, beneath ports that move goods for the entire global economy, beneath the daily lives of millions of people who wake up each morning, with no reason to think about what lies 700 miles offshore, locked in silence, waiting. Scientists cannot tell you when it will happen. They can only tell you, with newly rewritten certainty, that it will. And in the years since researchers first towed that sensor array across the ocean floor, in the years since a navigational mistake, revealed a hidden connection between 2 of America's most dangerous faults, in the years since a network of forgotten cracks was discovered running beneath an American city, the story of what lies beneath the United States has changed forever. The question was never really whether the ground beneath us is dangerous. The question is whether we will understand it in time, because somewhere, right now, beneath the quiet surface of the Pacific Ocean, the next chapter of that 10,000-year sediment record is already being written. We simply don't know yet what page we're on,